dive into chapter 2. What what questions do we have from chapter 2? Dealing with functions. Ava?
8 and 11.
Jenny, were yours before 8 and 11? Anybody have anything before question 8?
I had a question on 11, so.
Alright. So by the way, before we go there, a mapping diagram. Where is this? Maybe it's not. Yeah, here on the back. We'll talk about mapping diagram when we get there, but I think some of you guys don't know what a mapping diagram is. Once you know what it is, it'll be simple. But some of you guys you didn't know how to do it, and you just didn't do it. So 8 and 11. Let's grab 8 first. You just look at them if you want. Thank you, bud. All right, and the stem of this says, each set is a function. Write the rule that represents the function. Now, when we look at functions, we're trying to determine the rule. Setting them up like this is terrible. Now, some people can work like this, and they can deal with it better than I can. I can't deal with it like this. Absolutely cannot. I have to see things vertically. So the first thing that I have to do in this situation is make myself a T-chart. -7, -2, +3, +8, +13. Then the next thing we want to check, and they don't start to trick you normally till Math 2, but especially standardized tests, be careful with this. Check, what is your delta? What does delta mean? What does it represent in science and or math? Anybody? Change. So whenever you see this triangle, especially if I make notes on your tests, that triangle is delta. Means the change in. It is a Greek symbol. Yeah, know it, love it. We use it a lot. So the change in x, is it consistent? Yes. It is always +1 all the way down. Then evaluate what is your delta y. And we need to look at each delta y. So from -5 to -2, what, 5. From -2 to 3, from 3 to 8, from 8 to 13. So since my delta y is consistent, this first level change being consistent tells me this is going to be what type of function? A linear function. So then we know linear functions can be represented in the y = mx plus b form. What do I now know? Yeah?
That m is 5.
Your m can always be derived by your delta y over your delta x. Your change in y was 5 for every change in x of 1. This becomes 5x, but then I must also evaluate the b here represents our y-intercept, and our y-intercept is found by looking at the point where x is 0. For what it's worth, it is nicer to write the variable value first. So instead of writing -7 plus 5x, some people, like, depending on how you've been taught, just get in the habit of writing the constant first, because like you find your intercept and then you find your slope. It is better in mathematics we write the higher power of the variable first. So if we have like an x squared, that would come out in front of here. So say we have like a 3x squared, then a 5x, then a -7. We write them in order of their powers working down. But none of that exists here. So likewise in 11. Oh, I love 11. No matter what you're doing, if you have not done the Chapter 2 test yet, you should look at number 11 of the Chapter 2 test. Because this is notoriously... Now, if you know it, don't give it away. I've already talked with you about it. We've already met with this. Don't give it away. So go ahead and make your table. You have 10 ninths, 4 thirds, 2, 4, 10. Interessante. Looking at the change from 10 ninths to 4 thirds is like somebody asking you if you'd like battery acid in your Cheerios. It just doesn't look fun, right? Like, no, why? No. What could we do to make evaluating those two values easier? Ava, you had your hand up first. So. Find a common denominator. Yield, what should our common denominator be here? 9. So Jenny, what do I do to make that happen?
Multiply 4 thirds by 3.
So 10 ninths is going to stay 10 ninths, but then I get 12 ninths. While I'm at it, I might as well look at my integers as ninths as well. So 2 will become how many ninths? 18 ninths. 4 will become, and 10, this one's easy. Wow, that got so much easier, didn't it? No. I mean, it's slightly easier, but I don't think I would say so much in any stretch of the word. Man, so if I look at my changes, now that I'm dealing in ninths, this is easier. I went up by 2 ninths. Then I went up by 6 ninths. Then I went up by 18 ninths. Then I went up. What'd you say? Now, I wanted us to stare at this longer before we figured that out. Ignore the ninths, because those are all the same. I increased by 2. Then I increased by 6. Then I increased by 18. And then I increased by 54. So what I'm seeing here is not an addition like what we were initially looking at, but instead we're seeing a multiplication. And not that your output value is multiplying by 3, because it's not like 4 times 3, that doesn't work. It's not that the output is tripling. It's that the change of the output is tripling. When we see that the change of the output is a multiplication, that tells me this is going to be an exponential function. And exponentials are all in the form. So if you do not know this yet, I would go ahead and you could have a plus or minus c out here. You can always have a plus or minus c, some constant. Where do you think we put that 3 that we just found? That whole times 3 in the change, Jenny? It is not the x. Remember, the x is my input. My x has to stay my x. It's what term I'm on. It is the b. So this becomes y is going to equal some value, I'm just going to leave it blank for right now, times the change happening to my function, the times 3 to the change every time. Because this, to the x, says multiply it by 3 once, or multiply it by 3 twice, or multiply it by 3 8 times, or however far you've gone, you got to multiply by 3 that many times. Now what about my y-intercept then? We often, like we did in the last one, look at where does x equal 0. Well, here my x equals 0. That's a value of 2. What happens when when my exponent equals 0 for any base? This turns into a 1. So what would we need to do to make that work for my y-intercept? What if we add 1 here? If I plug in 0 and I get 1 here, and I add 1, I get 2. Now we still have yet to determine if I need something out here, so let's check one of my other terms. What about if I plug in 1? So x to the first, 3 to the first, going to be 3, plus 1 is 4. Well, that works. What about 3 to the second? What's that?
9.
Plus 1.
10.
Do we need anything here? You don't have to write it. That coefficient to my base just becomes a 1. If you want to be technical, coefficient, base, exponent, constant. Coefficient is the multiplier to any value. This is the base of our exponential, the exponent, obviously, and then any constant. So we can check the negative exponents. This is a good time to review negative exponents. Those will work out, but I just want to take a second to look at negative exponents. So what if we had 3 to the negative 2? Now, a lot of us, if we memorize the tricks, would probably be able to say that's 1 over 3 squared. But the y. What does a negative exponent, like y, and actually it's easier if we do this. Makes more sense if we do that. So if you memorize the rule, you know, put it on the bottom, make the variable positive. Why? Why do we use negative exponents? This is what I thought. I don't know if this is one of those lack of confidence because I'm in a room of people that I don't really know, or if this is just, I just don't know. Because a lot of people don't understand why we use negative exponents. Why do we use positive exponents? Let's start there. Like 10 to the 4th. Why do I use 10 to the 4th? What the heck is that telling me? We've talked like this whole time, I guess. I'm going to start paying Ava if you guys don't start participating. Yeah?
It shows how many times you multiply the number by itself, so it's like simpler than just writing out.
Now I have some friends that when I say the statement I'm about to say, like to tell me what I mean to say is lazy. But mathematicians are efficient. My friends like to say lazy. But mathematicians are efficient. We don't like to do anything, and you're all mathematicians right now because you're doing that. I actually have a degree there. We don't like to do anything that we don't need to do. Mathematicians are like the eternal middle schooler. Why? I don't want to. You can't make me. You can't make me write out those 10 fours, or those 4 tens. I'm going to write 10 to the 4th power and tell you I know what that means. This is how everything in math has come to be. Mathematicians just trying to make their lives easier. So, exponents just mean repeated multiplication. So if I had, I don't know, let's say 10 to the 4th, we already know, you already told me that means 10 times 10 times 10 times 10. So that one looks really bad. And then 10 to the 6, likewise, 10 times 10 times 10 times 10 times 10 times 10. What can be done here?
Get rid of all the 10s, like 4 on each.
Be careful saying reduce. I like that you didn't say cancel. Be careful saying cancel. A lot of people like to say, we can cancel these numbers. We reduce out to 1. We're trying to steer people away from the word cancel. So 10 divided by 10 makes 1. 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 So now on top, I actually have 1 times 1 times 1 times 1. Crap. On bottom, I have 1 times 1 times 1 times 1 times 10 times 10. I still have 10s down. So this really becomes 1 over 10 times 10. The negative exponent is used to represent repeated, essentially, division. But it's repeated multiplication in the denominator. So what this is really saying is divide by 10 twice. Instead of multiply by 10 4 times, divide by 10 2 times. Or this, divide by 5 6 times. Divide by 5, divide by 5, divided by 5, divided by 5, divided by 5. But yeah, so negative exponents are repeated division. But really, it's just repeated multiplication in the denominator, which how you guys learned it means that there were more 10s in the denominator than there were in the numerator. By how many? By 2. So, sorry, all that for negative exponents. Where did we even start with that? That came out of the exponential equation. Yeah. So if I plug in like the negative 2 here, 3 to the negative 2, that's really where I was trying to get. So let's say I plug in negative 2. 3 to the negative 2 becomes 1 over 3 squared, which is 1 over 9. 1/9 plus 1 will equal 10 ninths. So we can check it using those negative exponents. It still works out. What else? And you guys are not expected to do a ton with exponentials yet. You got to be able to identify when it's not linear. It doesn't mean it's not a function. It can still have function behavior, just a different type of function behavior. Yeah.
This is actually beforehand, but 22.
What about 12, 13, 14? Anybody with those? Did everybody get this? I feel like I was missing one person. And then, Madison, what is this? I can't quite read this. N-A-D-I. Oh, that's a dot. Okay. I just couldn't tell if that was like a letter or. Nothing 13, 14? Or 12, 13, 14? 15, 16. Oh, some mapping diagrams. Let's talk about these real quick. Some of you guys are gonna have a facepalm moment. Which, when I say if you don't know me, like a facepalm moment, I'm not trying to make you feel bad, but it's those moments where, like in life, you're like, oh. I know better. Like, I should have known. Like, it's not like a feel bad thing. It's just like a, really? It was that easy? Or I'm that stupid? Like, don't think you're stupid. You're not stupid.
That's all of those.
Sorry if this bothers you. The blue pen tip is mashed in, so it doesn't write very well because it's been used so often, so these tips are better. So when I swap the pens around, sorry if you're OCD and that bothers you, but I can't keep using the blue pen. It bugs me. So, a mapping diagram is as easy as this. What do domain and range mean? Someone not either. What do domain and range mean? Somebody not a Phoenix person. I want to say Caitlin, but that's not. Yeah, it is Caitlin, right? No. Crystal. Sorry, Crystal. Domain is input. Range is output. So when I input a -3, I output a 6. When I input a 0, I output a 2. Hey, this looks a lot like a T-chart, doesn't it? When I input a 1, I output a 0, and when I input a 2, I output a -3. You know how I make this a mapping diagram? And this is where you're going to hate me. It's okay. And you've now made a mapping diagram. Because every input maps specifically to one unique output. This is a function. When I check it for 16, I do the same thing. -1, 0, 1, 2, -4, 0, 4, 8, and check, is it a function based on its behavior? So a mapping diagram literally just says the -3 goes to the 6. The 0 goes to the 2. It's like matching up the input with its appropriate output. Questions? (17, 18) or 19, 20. Range is just the possible output values given the domain, so these are the input values. So you're going to generate 5 output values when you input these 5 values. 21? Waiting for that mean to die. Yes,
I have a
Jen?
question for like 17, 18, 19, 20. Like, when you write it down, do you have to write it from least to greatest?
No. Actually, my preference, crap, I'm writing on the PDF. My preference would be, it's actually working better than it has though. When I plug in -2, being that it's the first value in the domain, +4 + 1, I get a 5, right? I would want that to be the first one. 0 is the second domain value. I get a 1 from that. I'd like that to be the second range value. Like, it doesn't have to be, but it's easier to do it like that, and then you can honestly turn it into a mapping diagram by doing this. Now it's a mapping diagram. And I could keep going, obviously. Just don't want to give everything away. That has never let me write on the PDF that much. Surprised. Now I gotta figure out how to get rid of it. Are we good? Up through 20. So you said 22. Ah, thank you. I knew we'd need to talk about that. You're asking all the questions that I knew we would need to talk about. So I very much appreciate it. Explicit means we're going to drop all the swear words, right?
No.
What does explicit mean? What does explicit actually mean? Like in the sense of the word. Like if somebody gives you explicit directions, that does not mean that it had swear words in it. Yeah, like very specific, exact, precise. So, wait, what? Or what?
No, I got one.
So 21's easier than 22. So since Abe asked about 22, I'm going to do 22, but then leave 21 for you guys to do on your own. If I look here at what's happening, way too thick. Is this an arithmetic sequence? Well, to be arithmetic, it must continuously add or subtract. Arithmetic means addition or subtraction. So if you're not aware of that yet, or that's not clear, make yourself a little note. Addition is, or arithmetic is addition or subtraction. Geometric would be multiplication division. However, that's not even an option. Luckily, because that would just steer you down the wrong road. This is not arithmetic or geometric. So it is not arithmetic, right? We know that. Makes it a bit harder, right? So if I wanted to say a recursive is actually where we start. A recursive formula reuses the previous. So I'm going to say the number I just had plus something. So over here, I'm adding 4, adding 4, adding 4, subtracting 4. I would say the number I just had minus 4. That'd be the recursive. But we got to talk about how do I say the number that I just had.
Well, that's n, but it says that it's the sequence of arithmetic, so you have to do that, but it's not arithmetic.
Oh, yeah. So you actually get off the hook on this one. You can just write not arithmetic.
Okay.
I forgot where Math 1 we let you stop when it gets that hard. In Math 2, we'd make you write it out. So this would actually, for fun, if I want to say the value at term n will be the previous term, so we would say a sub n minus 1, that's how you say the previous term, plus, say n, the number of the term, so this is going to be term 2 added 3, so it'd need to be n plus 1, because then term 3 added 4, term 4 added 5. So this is going to say, like, let's say to get the 1, 2, 3, 4, 5, to get the 6th term, and you don't have to do this, I'm just showing it to you so you understand, and it might help you on 21. To get the 6th term, I use term 6 minus 1, so term 5. Well, what was term 5? Term 5 was 25. Plus the term number, okay, term number 6, plus 1 more, so plus 7. So to get to value of term 6, we take the previous term and add 7, and we would get 32. I would continue to do that, but recursive formulas are annoying because I can only move one step at a time. I have to know the previous value, which is where explicit come into play to say I can find the value at any moment. I don't need this previous term. So on 21, you want to write the recursive, something like this, depending on what's going on over there, and then an explicit, which is more like the y equals mx plus b, that sort of behavior. Yeah.
So when you write like the recursive formula, like the very end, like the answer, how would you like write it out?
It still involves a sub n minus 1. So it will still involve something like this.
So that would be the,
So let me check if I had this in Schoology or not. Is this chapter 2?
Yes.
We don't really do much with recursive this year. It's really like an intro so you understand what it means. It's kind of one of those, we don't expect you to use it this year. Where our textbook material stopped was really explicit definitions of an arithmetic sequence. So this is your, drag this up here. So that's your rule that you want to use when trying to formalize the arithmetic. So, yeah, that's the problem sometimes when you click, it takes you into the folder. So since we know that 21 is arithmetic, I can just use that formula. So the value of my term at n, and they can either say a sub n or a of n. Those are the same thing. A of n, a sub n mean the same thing. The first term, a sub 1, plus n minus 1 times that common difference of a minus 4. Now this is not cleaned up yet, though. We then can distribute this and say this really becomes y equals mx plus b. This is your slope, or the change in your function behavior. This is your y-intercept, or where your, or what your output value would be at term 0. Think about when x equals 0, our y-intercept is at term 0. If this is term 1, then there is some term 0 out before that that has the same behavior. Well, I was going down by 4, down by 4, down by 4. So if I go the other direction, like up by 4, up by 4, up by 4, term 0 is 19. That's my y-intercept. It's just y equals mx plus b.
That's explicit.
That is explicit. So, like, I'm really not going to be that critical with the recursive. We might as well do this together since recursive is a really weird idea. You'll be expected to do this in Math 2. We come back to formulas and we do a lot with recursive in Math 2. I teach Math 2, by the way, like through the normal school year. So if you want to see any Math 2 stuff or discuss like where the differences Math 1 and Math 2 are, we can chat about that. But if we look at 21 still, I could say to get the value, so a of n or a sub n, I take the previous term and do what to it? For that function over there, 15, 11, 7, 3, you subtract 4. That's your recursive. Seriously. That's all you do for recursive. The previous term and the behavior that happens. Any other questions on these? Yeah. 25. So the problem is, these open-ended questions, there's like infinitely many responses that are correct. It all depends on how crazy you want to get. I have an odd sense of humor, if you haven't figured this out yet. And I discovered this when I was a kid. And this is why I have to just like smile at some of these middle school behaviors. And this is why I work in the middle school. Because I was that kid that was always trying to like stretch the rules and stretch the whatever and like try to find other ways. And I'm also one of those, like, if you don't get caught, it's not breaking the rules. But all it says is 10th term is 75. And it's arithmetic. That's all it says. So all I know is this has to be some form that is continuously adding something. And it can start somewhere if we want. So the easiest thing that I could think of is, what if I start at 65 and add 1 for every step I take? On the 10th step, I'll be at 75. Now, one thing that throws people off is they set up a multiplication and they say, well, that doesn't add every time. Well, what would 5x do? Well, that would say add 5 for the first step, add 5 again, add 5 again, add 5. So when you set up a y equals mx, this is really arithmetic. Then you just tell it where to start. Well, 10 steps here would get me where? 10 steps going 5x. 50, right? So I could just add 25. I could also not have an initial starting point. How big would my step need to be to get to 75 in 10 steps? There's infinitely many ways that you can play this out. This will work, this will work, this will work. Like, it's all just how you think about it. I could start at 70 and take steps that are only half, like 0.5x. I could start above 75 and do a negative step. Many, many options here. Anything else from all of chapter 2? I totally forgot, by the way, about breakfast. Was anybody meaning to go get breakfast today? So there is, I'm going to go ahead and stop this video.